In this recording, we will talk about exponential functions and their definition. The standard definition found in most textbooks is the following one. Exponential functions are functions defined by a formula of the form f of x equals to a constant, let's say c, multiplied by another constant a raised to a power x. The disadvantage and probably frequently frustrating aspect of this definition is that it doesn't really tell you anything about these functions unless you already know something about functions of this form. A better definition and a key property of exponential functions is that exponential functions are functions that change their values at a constant percentage rate. In order to understand what this means, let's take a look at the following example. In this example, a quantity Q increases by 30% every 5 years. For example, this could be the value of an investment account that pays compound interest. We are asked to write an equation for Q in terms of time t in years. The initial value of Q is capital A. In this example, we have a quantity that increases at a constant percentage growth rate. So why constant? Well, it's because it doesn't matter which period of 5 years we look at, the first 5 years or any other period of the same length of 5 years. Over any such period, the increase in the value of Q is going to be the same 30%. In order to see what equation describes this growth, let's make a table. We start with, in the first column of this table, we have t values. In the second column, q values. And we start with t value equal to 0, q value equal to a. 5 years later, the q value is going to increase by 30%, and it will become a plus 0.3 times a. In other words, a times 1.3. After another 5 years, when t equals to 10, the value of Q is going to increase again by 30%. Relative to what? Well, relative to the start of that second 5-year period, and the start of the second 5-year period is t equals to 5, when the Q value is equal to a times 1.3. So at t equals to 10, after 10 years, the value of Q will be a times 1.3 multiplied by another factor of 1.3, which of course gives us a times 1.3 squared. Another 5 years goes on, and at the end of that period, when t equals to 15, our value of Q will become a times 1.3 squared times another factor of 1.3. In other words, a times 1.3 cubed. And so on. You can write as many rows as you like. And our goal is to come up with a formula that would give us Q value for any value of t. Right? So the question mark, we need to find a formula that we could use here in place of this question mark. One thing that we can see from this table is that the Q value is always a multiplied by a power of 1.3. Okay, so now we can write that our formula will be something like this. Q of t equals a times 1.3 raised to some power. And now we need to determine what to put in this exponent. What power do we have to raise 1.3 in order to get our correct q value? Well, let's look at these exponents. So when t equals to 0, the q value is just a, and we can think of this as, looking at this a, we can think of this a as a times 1.3 raised to the power 0, right? Because 1.3 raised to the power 0 is 1, and a times 1 is just a. When t equals to 5, we have a times 1.3 raised to the power 1. When t equals 10, we have a times 1.3 raised to the power 2. When t equals 15, the exponent is 3. When t is 20, the exponent is 4. So now we can see from these calculations that the exponent in this formula has to be t divided by 5. And so we take that and we input it into our formula, and our final result is q of t equals a constant, times 1.3 raised to the power t divided by 5. So you can see that that is an exponential function as defined by that definition that I started with. Well, in fact, you can perhaps subject here a little bit, because if we go back to that definition, you might say, well, in this definition of an exponential function, the exponent has to be just x, just the variable. Here we're using t as our variable instead of x. That's not a big problem. We can use any letter. But perhaps you might say, well, the exponent here is t divided by 5 and not just t. So is this an exponential function? Well, we can actually, it sure is, and we can actually rewrite this in the following form. A times 1.3 first raised to the power 1/5, and then all of that raised to the power t. And we can think of 1.3 to the power 1/5, whatever that number is, as our lowercase a, the base of that power that was used in the definition of an exponential function at the start of this recording. Okay, and so I'm hoping that this example shows that a constant percentage growth rate leads us to an equation of this form.